Hey, good morning, everybody. Would one of the learning assistants please confirm that they can hear me?
Yes.
Thank you. Okay, so today I'd like to start with just a few announcements. So homework one that you just completed last night was a fairly short assignment because we had covered very little material last week. But homework two is going to be regular length. The average time that it takes people is roughly 2 hours or so. So please be sure to leave adequate time for doing it. And starting today, I'll be giving extra credit, provided that there's at least one good question that is asked. The Penn State user IDs starting with WQ through ZZ are the ones that need to ask at least one good question in order for this extra credit to be applied. And generally speaking, I will provide the first two letters for each class up in the upper right-hand corner of the slides. That said, anybody, of course, can and should ask questions, and please do so by using the chat. I probably won't be able to answer the questions that I see in real time, although often the learning assistants are able to answer. I do look at the chats afterwards, and if I see some questions that I think would benefit from me answering them, I'll typically answer them on PHYS, which is the question and answer site link. The link for Physics 214 is given here, and it's also linked to the Canvas course page. That's a good place to post questions that you might have about homework or other material, and other people besides just the instructors, learning assistants, TAs, other people, yourselves included, can answer questions there. Okay, so today we're going to talk about two-slit interference, then discuss what happens when light goes through just one slit as opposed to two. Then what happens when light goes through a large number of slits at the same time, a large number of identical slits. And finally, how such a device could be used for chemical analysis. That device is called diffraction grating. Okay, so last time we started talking about how light would interfere coming out of two slits. And what happens is the light comes in from the left-hand side. It goes through two slits, and then the light coming from one slit and the light coming from the other slit can interfere with one another and cause a pattern to be seen over on a screen at some reasonably far distance away. And if you look more carefully, the extra distance that that light travels from one slit, so along path R1, versus the distance it travels along path R2, is given by this little extra bit right here that I'm highlighting in blue. That extra distance is given by D, the spacing between the slits. So this distance here is D, times sine theta, where theta is this angle, which is the same as that angle there. So along path R2, there's an extra distance d sine theta that light will have to travel. And so if you want to get constructive or destructive interference, what you ask for is that that little segment be either an integer multiple of wavelengths or a half integer multiple of wavelengths to get constructive or destructive interference respectively. So if, for example, this distance here is one extra wavelength, then that means that the light that travels along R1 will have traveled, say 10 wavelengths, and the light that travels along path R2 will have traveled 11 wavelengths. And then when they meet at the screen, they will constructively interfere because one just gets shifted by a full wavelength compared to the other. And so the peaks will still line up with the peaks. troughs with the troughs, and they'll add up constructively, fully constructively, at the screen at this particular angle theta. And just so it's clear, what's meant by this angle theta is if you draw, if you imagine a horizontal line that is perpendicular to the plane that holds the two slits, that defines theta equals 0, and any angle away from that is an angle theta. Okay, so that's the definition of that, that angle theta. All right. Now you can also look at what's happening at the faraway screen, where far away here is some distance L, which is, maybe a meter or something like that. And what we want to determine there is this bright fringe at some angle theta. So the light is coming out of the double slit, which you can't even see over here because it's so small compared to this distance L. But the light coming out of the double slit is, let's say it's constructively interfering. So we see a bright fringe right there. The question is, how far from the central axis is that bright fringe? So what is this distance here, y? And the answer is that it's equal to L tan theta, which you can see if you just do the basic trigonometry. The distance L is the distance from the double slits to the screen, and theta is the angle that we're interested in. And so this value y, the distance from the central axis to the position of interest, is given by L times tan theta. All right, so let's apply that. So what I'm showing here is the figure that we had from before on the right. And I don't know if you look at the screen right now, what we have with this screen is you're looking at it edge on in the picture on the slide. And what you're seeing over here is what it looks like when it's facing you. Okay, so that's the relative orientation. So again, the figure on the right, you're looking at the screen that has the interference pattern on it, edge on, and then the lower left-hand figure with the bright fringes is what you see if you're looking at it face on. So the question here is, what is this distance between the fringes? So in order to do this, we're going to need to figure out a general expression for delta y. So if, let's say, this is y sub m and this is y sub m plus 1, what can I write for delta y? Can anyone answer that in the chat? Anybody? So right, it will be y of m plus 1 minus y of m, or y sub m, I should say. So what we get then is if we plug in m plus 1 into this expression and then plug in m into that expression and take the difference, we'll get what delta y is. So in other words, we'll have m plus 1 times lambda L over D minus m times lambda L over D, like so. And you can do that algebra pretty straightforwardly. You will just get lambda L over D. So that is the distance between two of these fringes. And you can see that they're regularly spaced, as you would expect from this formula. So the distance between any two of these is given by lambda L over D. Lambda is just the wavelength of the incoming light, which is a constant in this case. And L and D are both parameters of the configuration that we've built this experiment. L is the distance to the screen, and D is the distance between the slits. That's also constant, so we see a constant offset between these two, between any adjacent fringes. It's equal to lambda L over D. Good. So next, I'd like you to work on this concept question. I'm going to set up a poll so that you can answer this question. So let's first look through it. So if we set y sub m equals m lambda L over D, that'll give us constructive interference, because then we'll have an integer number of wavelength difference between the upper slit and the lower slit for the distance that the light travels. And then we'll get, if they're offset by one wavelength, we will get constructive interference. So what would be the corresponding expression for destructive interference? And what you should focus on is, this little extra distance here, which is given by d sine theta. If that's equal to an integer number of wavelengths, then we'll get constructive interference, because then when these two waves traveling a distance r1 and r2 travel to the screen, when they arrive there at this angle theta, they will be offset from one another by an integer number of wavelengths, and they will constructively interfere. So what's the condition for destructive interference?
Can you quickly show that equation again?
Which equation?
The one you pointed out just now on the previous slide.
This one?
Yep, thank you.
Yep. Okay, get your answers in, please. All right. So most of you answered B, which is the correct answer. So the destructive interference condition is that we should have a half integer number of wavelengths along this extra little distance, delta R. So this condition given by answer B tells you that, say, if m equals 0, you'll have half of a wavelength difference. If m equals 1, you'll have 3 halves. If it's 2, you'll have 2 plus 1 half is 5 halves, and so on. So the number of wavelengths, additional wavelengths that's traveled by the lower wave, in this case, relative to the upper one, is a half integer. So that means that when these two waves arrive at the faraway screen at some angle theta, if one of them has traveled a distance lambda over 2 farther than the other, then the peaks will line up with the troughs and the troughs with the peaks when you are at that faraway screen. And so the two waves then will cancel each other. And a similar thing for 3 halves lambda or 5 halves lambda and so on. And in each of those cases, you will get fully destructive interference, which will produce a dark fringe at the faraway screen. All right, so let me work through this example here, where I have a double slit experiment, and it's performed with light that has a particular wavelength, 600 nanometers. And by the way, we're going to use this unit quite often in this class. 1 nanometer is 10 to the minus 9 meters, in case you didn't know. The bright interference fringes are spaced 1.8 millimeters apart on the viewing screen. So what will the spacing become if the light is changed to have a wavelength of 400 nanometers instead of 600? So we have, we're trying to find delta Y. We're given that it's 1.8 millimeters in the first case. And the expression for delta y, which we wrote down before, is yn plus 1 minus y sub m, which is equal to lambda L over D. Now, if you just look down at this expression given down here, you can figure that out just like we did a couple slides ago. And by the way, parenthetically, I just want to mention that just like on this slide, the relevant equations that you're going to need are given on the quizzes and the final. The formula sheet will be available. You will have equations like this right in front of you, so you won't need to memorize the equations, but you will need to know conceptually what's going on in each problem so that you're able to apply these equations in the correct manner. So I strongly discourage you from trying to like throw equations at a problem and see which one sticks. It's much better to try to understand the problem conceptually first and then figure out which equation is the right one to use to arrive at the answer. All right, so anyway, we are given here that delta y is 1.8 millimeters. We're also told that the wavelength is 600 nanometers. So it's useful usually with problems like this to write down all the things that you're given. And then we know that delta y is lambda L over D. So if I look at these, the things I have here, I can write that 1.8 millimeters is equal to, so it's 1.8 times 10 to the minus 3 meters. And that equals lambda, which is 600 times 10 to the minus 9 times L over D. Now I don't have L over D. I have neither L nor D. But actually I do have L over D because I can solve for L over D here. And if you do that, you'll get that L over D is 3000. Now that's not what the question asked for. The question asked for what happens if the light wavelength is changed to 400 nanometers. Now, if you look at this original expression that I wrote down here, delta y, just rewrite it over here, lambda L over D, you see that L over D appears here. And you should realize then that these two things and their ratio do not change. So all that I'm changing is the wavelength of the light that is going into this two-slit experiment. If the two slits, if I draw the experiment, are over here, and here's the screen, so this distance L stays the same. This distance D between the two slits also doesn't change. So those two quantities stay the same, their ratio stays the same, and therefore what I can do, if I want to find out what delta y is for 400 nanometers, I would just put in the 400 nanometer wavelength times the L over D, which is 3000. And if you do that, the answer you'll get is 1.2 millimeters. So here, the work is shown a little more neatly than my chicken scratchings. So you see that we use the fact that that L over D is a constant, and we use that down here with the new wavelength to get the new spacing. So when we change the wavelength, leaving everything else the same, when we made the wavelength shorter, the spacing between the fringes got smaller. So the whole pattern basically compressed on the screen. Okay. So the next thing I'd like to cover is single slit diffraction. Diffraction is what happens to a wave when its wavelength is comparable to the opening through which it is traveling. So in the case of light, we're going to talk about the slit width and say that it's comparable to the wavelength of the wave. A more common everyday experience is, say you're standing in an empty hallway, and that hallway sort of joins with some other hallway at 90-degree angles, and someone is in that other hallway. You can't see them, but they're talking, and you can hear them even though they're not pointing directly at you. So the sound that comes out of their mouths actually literally bends around the corner of that hallway due to diffraction. So it's the sound is diffracting around the corner, and so you're able to hear somebody even though they're not in a direct line with you. And in a similar way, when light goes through a very small opening, so when the example I just gave of the sound wavelength is pretty big, and the opening in the hallway is comparable to the size of the wavelength of sound. In this case, we have the same condition applying, namely that the opening has to be comparable to the wavelength, except now the wavelength is really tiny. You know, it's 100 nanometers or so instead of, you know, a meter for sound. So the slit width is going to have to be quite a bit smaller in order to be comparable to that, obviously. What you see then is the pattern on the viewing screen that's shown in the figure on the right-hand side of the slide. What you don't see, if, for example, there were blue light coming through, what you don't see is a pattern that basically, I don't know if you can see it on the screen there, I just drew essentially an outline of this slit here appearing on the screen. And that's because the slit width is comparable to the wavelength, so you get diffraction effects. And instead of seeing just sort of the shadow of the slit, you see this pattern because the light, when it goes through the slit, spreads out, it diffracts. And it causes the pattern that you can see on the screen as shown in the figure. In order to determine quantitatively where the fringes on this pattern occur, what we're going to do is use a model that gives us the right answer, but the model is not, it's not really physically driven. The formula or that model can actually be derived from a more complex formula, but we're not going to go that deep into this here. We're just going to assume that the model works and use what it produces to understand and to predict, I should say, what the pattern will look like when light of a wavelength comparable to a slit width goes through the slit and diffracts. So the principle is called Huygens principle, and I'm probably pronouncing that wrong. It's a Dutch name. The basic idea is to treat a single slit as a set of many in-phase emitters of spherical waves. So what does that mean? So that means that there are lots of little emitters that I'm imagining here, and they're each producing waves coming out. And I'm not going to draw them all because it would get pretty messy really quickly. But all of these spherical waves then interfere with one another. So what do we get as a result of that? In particular, what is the condition for the first dark fringe or fringes sort of above and below the central maximum due to destructive interference? So what I mean by that is right here at the central point, just here, we expect to get a bright fringe because each of the rays, if I imagine all these rays coming from all these different points, will have traveled essentially the same distance in order to get to that central point. And so we will get a large bump right here in the center. If we go off center, at some point, we're going to have the destructive interference condition met. And what that means is the following. So let me just try to clean things up a little bit here so I can better explain things. So if we look at these one pair of these emitters shown with the two remaining blue dots here, so here and here, the light that comes from those two blue dots travels along the two dashed lines to some point over here on the screen. In order for there to be destructive interference over there, what we're going to do is basically what we did for the two-slit interference pattern, but now remember we just have one slit. So we're going to drop down a perpendicular line, perpendicular to this lower line, and say, what is this extra distance that the lower wave travels compared to the upper one? So how much farther, if I look at R1 and R2, how much farther do I travel along path R2 than along path R1? If I want destructive interference at this point over here on the screen, then I'm going to require that R2 travels a half integer number of wavelengths farther than along R1, because then when the two waves meet at that point on the screen, the peaks will line up with the troughs, troughs with the peaks, and we'll get destructive interference. So what is that condition? How do I write that down? So the basic condition is similar to what we wrote down before. We look at that little delta R that I highlighted before. That's the extra distance that R2 travels relative to R1. That delta R is going to be given by A over 2, where A is the slit width opening. So remember, we're just looking at this point here and this point here, just below just at the opening at the very top, and just above the midpoint, or maybe right at the midpoint. Those are separated by a distance A over 2. And if you do the trigonometry, you'll see that delta R is A over 2 sine theta, and then we set that equal to lambda over 2. If it's equal to lambda over 2, then we'll get destructive interference over here, which is what we're trying to do. Okay, so that condition, we consider just those two waves coming from the top and middle of the slit, is basically A sine theta equals lambda, because those twos just cancel in the denominator. And then the question is, how do we extend this to cover the entire slit? So if you look at this picture again, we did it for these 2 points here and here, that pair of points. What if I move just a little epsilon down vertically to the next set of points? So just here and here, and did exactly the same thing. At exactly the same angle, the delta R for the rays coming from those 2 points is going to be the same as the delta R from the upper 2 points. So, I mean, if I drew that in, you know, here's one set of dashed lines, another dashed line, and then this distance here, that will also be delta R. And I can keep doing that for pairs of points until I get all the way down to just above the midpoint and at the very bottom. So that's the very last pair of points. And I'm asking that every single one of these pairs of points satisfies this condition. And if that's the case, then they will all destructively interfere. Every single pair of points will destructively interfere at the far screen, or I should say, every single pair of points from which light is traveling, when it reaches the screen, will destructively interfere. So that's going to give us the overall condition for the first dark fringe. So that's what I wrote down just a minute ago. A sine theta equals lambda. Now, if you want to find the second dark fringe, so here's the first one here. There's a bright fringe right there in the middle, and a dark fringe. If I keep going, if you keep looking, you'll see that there's another dark fringe out here, and it keeps going. So this was just the first dark fringe here and here. So this is number 1. And here's number 2, above and below, and so on. So how do we find where number 2 is? And the way we do that is, instead of splitting the slit into halves and looking for pairwise emitters, we split it into fourths. And if you do just the same exact procedure that we talked about before, then you'll find that the condition is now A over 4 equals lambda over 2 for destructive interference. And you can rewrite that as A sine theta equals 2 lambda. And the way this generalizes is A sine theta is equal to P lambda, where P is 1, 2, 3, etc., an integer. So I need to emphasize that this is for diffraction producing dark fringes. This is where the dark fringes are, where we get destructive interference from a single slit. A sine theta P equals P lambda. And P is 1, 2, 3, etc. It's not 0, because at 0 we get a bright fringe. So that's at the center. So this is off from the center. If P is equal to 1, we get the first dark fringe above and below the center maximum. So if I draw that center maximum again, so here, this. So this is the central maximum right here. And then here is P equals 1, P equals 2, and so on. And down below, it's symmetrical. P equals 1 here, P equals 2, and so on. Notice that it looks very similar to the expression for two-slit interference, which is d sine theta sub m equals m lambda. But that expression is for bright fringes, for double slits. So be very careful to keep these two separate. So effectively, with single slit diffraction, what we did was we treated these two slits, this one slit, as though it had an infinite number of openings. And we were looking at the openings pairwise for the very first interference, for the very first diffraction minimum. And then we were looking at it, I don't know what the right term is, like quarter-wise. We looked at pairs that were separated by a quarter of the distance instead of half the distance. And by doing that, we end up getting this expression that tells us where the dark fringes are located. Whereas with the two-slit experiment, we were looking at the waves coming out of just two slits and saying that they will interfere constructively when the path is different from one slit versus the other by an integer number of wavelengths. And so that's why we got this expression here. So even though those expressions look similar, they're for two different phenomena, related, but different phenomena. And one of them is for dark fringes and the other one is for bright fringes. And that's because of the geometry of the situation. Okay. So let me give you this concept question here on single slit diffraction. So the question is, we found the dark fringes by doing the procedure previously wherever there was destructive interference. Can we use a similar procedure to find the position of bright fringes? So the procedure we followed was we set this delta R, shown over here, delta R12, equal to a half of a wavelength, and then 3/2 of a wavelength, and so on. And by doing that, we got pairwise destructive interference. So the question is, can we use a similar procedure where instead of setting delta R equal to lambda over 2, we set it equal to lambda? Would we then get the positions or an expression for the positions of the bright fringes? Okay, please get your answers in. All right. So most people answered A, which is an entirely reasonable answer. Unfortunately, it's not quite right. And the reason that you can't use pairwise constructive interference is kind of subtle. So let me go through it here. It's an important argument to understand. So if you look at the figure, I've got two delta R's labeled, delta R12 and delta R34. And delta R12, this distance here, is the same as this distance here, delta R34. And we could, in principle, set them to be one wavelength and say, okay, in that case, the pairwise rays are going to constructively interfere, and therefore I will get a bright fringe by applying the condition that A over 2 times sine of theta equals 1 lambda. The problem is that you need to look at what happens with other pairs of rays. So other pairs of rays could be destructively interfering, while the pairs that you look at are constructively interfering. So I've shown here delta R13 and delta R52. And those could be half a wavelength, in which case those guys will destructively interfere with one another. So simply because you get some pairs to constructively interfere doesn't mean that other pairs won't partially destructively interfere. That's not the case with the destructive interference. If you get pairs to destructively interfere, then they're basically, removed from causing any problem with any other pairs, right? So you get each pair to destructively interfere. The net effect is that you're going to have a dark fringe and destructive interference if you add up the infinite number of pairs in this single slit. But the same argument doesn't hold for constructive interference, because if you get a pair that constructively interferes, like pair 1 and 2, 3, 4, and 5 and 6 here, you could get other pairs that are destructively interfering. So another way of looking at this is with vectors, and that's shown in this lower right-hand diagram. So the first case where we get pairwise destructive interference, each pair of vectors cancel with one another. So you get effectively this is equal to 0, this is equal to 0, and this one is equal to 0. And if you add up 0 plus 0 plus 0, you get 0. So having destructive interference be required for each pair means that when you add up all the pairs, you will also get 0. You will also get destructive interference. They will cancel with one another. By contrast, if you ask for pairwise constructive interference, so I can say here that this equals 1, okay? I'm just using 1 to say there's constructive interference. And this one is also equal to 1, and so is this one. But if you look at those 3 pairs of vectors and you add all 6 of them together, you will get 0. So even though pairwise you're getting constructive interference, it could be that the pairs could cancel with one another when they're added up. So while the top case works for giving us destructive interference positions on the screen, the same argument cannot be used to get the bright fringes where there's constructive interference. Because that second condition, where you ask for constructive interference, you could end up overall with destructive interference when everything is added up together. That said, if you can find in a diffraction pattern where the dark fringes are, using the methodology that we've just gone through, then you can find where the bright fringes are by saying it's in between 2 dark fringes, because in between each pair of dark fringes on the screen, there will be a bright fringe. So it's kind of an indirect way of finding where the bright fringes are in a diffraction pattern. All right, so let me work through this example of single slit diffraction. So in a single slit experiment, we have a slit width that is 200 times the wavelength. So A equals 200 lambdas, writing that down. And we're trying to find what the width is of the central maximum. And it's on a screen that's 2 meters. So this L here is 2 meters behind the slit. So in order to work through this problem, after writing down the things that are given, you realize that you can just use the expression that y equals lambda L over A. And that will give you L over 200, or 2 meters over 200, which is 10 millimeters. Now notice that what you've solved for here is this value of y1 shown in this figure. But what you're asked for is the distance from here to here with W. So that's basically double the y1 we just calculated. So it's 20 millimeters. Okay, so let me just summarize this by saying that what we typically have in an actual, experimental situation is a combination of 2-slit interference and 1-slit diffraction. So typically a 2-slit interference experiment will have 2 identical slits, and those slits will be pretty small and not separated by a great distance. So you'll have both interference and diffraction effects. The diffraction effects from each slit will be identical because each slit is usually the same width and so on. So the visual summary would look something like this. There's a 2-slit interference pattern shown by the figure at the left. And that's idealized because we're assuming that there's no single slit diffraction. But of course there is single slit diffraction, and it looks like this. And I've drawn 2 figures here because there are 2 different slits. And this is all just like schematic here, so don't take this all too literally. And effectively what we do is we multiply the 2-slit interference pattern by the single slit diffraction pattern going through each of the 2 slits. And what we end up with is this final pattern here, which has the 2-slit interference pattern underneath. That's the fast wiggles here as it goes back and forth. Underneath what's called an envelope. So I'm drawing it on here. Here's the envelope due to the diffraction pattern. And one thing that you can see, and it's I believe it's a problem in the homework, is there are going to be places where the diffraction pattern has a dark fringe, but the interference pattern has a bright fringe. And in those places, darkness wins. So dark fringe is basically, a 0. And so you multiply anything by 0, you get 0. And those are places where what's labeled on here, what occurs is something called a missing order. So the order M is shown in this figure. So you might, here be missing the 6th order. So this particular bright fringe that I'm outlining here gets knocked down by the first dark fringe of the diffraction pattern, and you end up seeing 0 where you would normally have seen something. And in fact, you can see that the diffraction pattern is because it's producing this envelope. So instead of having this nice uniform intensity pattern all the way across the screen, you have this this pattern here where the only place that it's at the maximum is right here at the center. everywhere else, over here, etc., it's being depleted by this envelope here, or this envelope here, the same thing. And where the diffraction minima, say at p equals 1, occurs, you will see a missing order or no interference bright fringe there because it gets zeroed out by the diffraction dark fringe. All right. So what I'd like to do next in the remaining few minutes is talk about an application of this idea, something called the diffraction grating, which really should be called an interference grating, because what's really going on is interference. Although diffraction does happen, interference is the main effect. So it's basically what happens when you take a double slit experiment and you make, instead of 2 slits, n slits. You can also have what's called a reflection grating, where instead of having lots of slits, you have lots of grooves very near one another. So what happens when a plane wave passes through these slits or bounces off of this of these grooves? So that's illustrated here. The spacing between each slit, and there are many of them shown here, is d, and at some angle theta, which is shown here using the normal definition that we're accustomed to from 2-slit and 1-slit experiments that we've just been discussing. At some angle theta, the extra distance that light travels from the I+1 slit versus the ith slit is d sine theta. So that's just shown right here, this extra distance. So here is, s sub I, and here is the I+1 slit, here and here. And then you can see that this pattern repeats itself. So if I look at I+1 with the I+2 slit, I get the same d sine theta distance, extra distance traveled by the light coming from the lower slit relative to the upper one, and so on. That applies for the entire grating as we move down it. So what's the condition then for constructive interference? Well, we're going to just require that the distance that the light from the ith slit travels relative to the I+1 slit is an integer number of wavelengths. So another way of writing that is saying, okay, this d sine theta m, which is what this delta r is over here, is just equal to an integer number of wavelengths, or m times lambda, where m is an integer, 0, 1, 2, etc. And just as for the 2-slit case, you can also convert this to a statement of what's the distance along the screen, y sub m, by using the relationship between the distance to the screen and the tangent. And here m is called the order of the diffraction grating. So the higher this value of n, the narrower and the brighter the fringes, and basically the better the diffraction grating is. So what will happen if you send at the same time plane waves from 2 different lasers with 2 different wavelengths through a diffraction grating? So the first thing that you'll notice is that at the central maximum, whoops, don't know how to undo this. There we go. At the central maximum, right here, all the colors line up. They fall on top of one another. But as you move off of the central maximum, because if you have, say, blue light coming in and violet light coming in, the 2 peaks at the m equals 1 order, so this is m equals 1 here, will be separated. And you can see that maybe best on the screen. So there's some distance between those 2 peaks because they're different wavelengths. And that's because if you look at this expression here, this theta depends on what the wavelength is. So for a given M and a given D, the distance between these gratings, if you change the wavelength, or if the wavelength has changed, you will get a different angle theta. And so that's what you see right here. So this is at one angle theta for this fringe, and this purple fringe occurs at a slightly different angle theta. So even if you couldn't tell that there were two different colors there, in this case you can, but if you had two wavelengths of light that were very close together, they could look to your eye like they were identically, you know, they were both yellow. You wouldn't be able to tell that there were two different yellows coming into your eye. But if you sent that light through a diffraction grating, then if it's a good enough diffraction grating, it can separate out. So you would see two bands of yellow on the screen, and you know right away from that that there must be two different wavelengths of yellow light being produced by whatever this source is. And this is a way that diffraction gratings are used to do spectrography, not sure what the word is. Basically, you can use the light coming out of a chemical sample, for example, to figure out what is in that sample. Okay, looks like I've run out of time. So next time we'll do this concept question on diffraction gratings and a mercury lamp. Okay, thanks very much, and see you next time. If you have any questions, I'll stick around for a few minutes. Happy to answer any. Take care. Bye-bye.
Bye, thank you.
Sir,
Yes.
I am having a pretty serious problem getting signed up for the homework, the Mastering Physics.
Okay.
Like whenever I try to log into the course, do you mind if I screen share?
You can screen share. I am pretty sure I will not be able to diagnose your problem, though. My suggestion would be the following. Did you try looking at the link to figure out possible browser problems? Because that is typically the reason why people have trouble accessing Mastering Physics.
Tried 3 different browsers.
Oh, really?
Yeah.
Okay. I think the best thing for you to do is to send an email to Dr. Van Hook. Because I apologize, but I just am not familiar enough with the system to be able to help you.
Okay. All right.
Thanks.
Thank you very much.
Yep.
Hey, Professor, I have a question. About
Sure.
that last, the last slide that we were looking at. Yep, that one. So I saw one earlier where the one that you draw with the graphs. So it goes really high intensity in the first one, and then it starts decreasing. I was wondering if they decrease like with a constant number, and then they just stay the same because they look like they stayed the same, or they like decrease linearly as far as you go from the center. Because here they look kind of equal. So like I'm not sure how they decrease. I'm like even the distance between the M1 and M2 up there looks like they're changing as well. How do you figure out all that?
So are you asking, let me see if I can find.
Yeah, that one.
Yeah, so here you see that you're saying that, well, the central max is huge, and you know, right over here, the very one next to it is much smaller. But then when we look at these diffraction grating patterns, all of these look like they're roughly the same height.
Yeah.
Okay, that's a very good question. So that's one of the advantages of diffraction grating is that if you have a very large number of slits or grooves, then the intensity at each order as you move away from the central maximum does not decrease as quickly. So basically what you're what the diffraction grating does is it sends the light at a particular wavelength at a very, very particular direction. So the peak is very, very sharp. And so, which is another way of saying that like this peak right here is very narrow. Okay, so this width here is small. And because of that, it can still be quite bright. still have a pretty high intensity. So it does decrease, and you can see here that there is sort of a gradual decrease as we move away, but it's much less pronounced than with the normal diffraction pattern that you just saw a second ago.
So N is directly proportional to intensity, light intensity, pretty much, right?
Sorry, can you say it again, please?
And the number of slits is directly proportional to light intensity, is what you're saying, right?
So
So
I'm not sure I heard you right, but the intensity goes as n squared, turns out.
Oh, okay. So the bigger the number of N or number of slits, the higher the intensity, right?
That's right. And the narrower the peaks.
Okay, I see. Sounds good. Also, I had another question. I asked Dr. Van Hook, I sent an email as well about the lab section. I
Yeah.
wanted to reach Miss he told me about Miss Wallach, get into contact with her. I was wondering how I can reach her still, because I need to change my lab before this week's lab, so I can attend that.
So I think that contact information is probably somewhere on Canvas, but if you can't find it there, then
I sent him an email asking about it a couple times, but I didn't get an answer.
all right, send me the email, please, and I'll follow up on it.
Okay, Professor Cohen, right?
Yes.
Okay, will do. Thank you.
You're welcome.
Have a good one.
You too. Bye-bye. Any other questions?
I have a question regarding how you determine the change in path length for the light that comes in at an angle through the slit.
Okay.
Or
Are you talking about interference or diffraction or either?
like at the very beginning when we were talking about the double slit experiment.
Okay, here.
Yeah. If they're both, the slit is the L distance from the wall and they're both going, or both rays are angled at some angle theta.
Yeah.
How are they different distances to the wall?
So first of all, so this distance here is equal to what?
D.
Right. And that D is going to be tiny, okay, compared to how big the fringe is on the wall. So the only thing you need to worry about, so these two rays are going to end up effectively at the same place on the screen, separated by a tiny little distance d if they travel in exactly a straight line. The one that's below this R2, labeled R2 versus R1, is going to travel this extra distance in order to get there. And that extra distance is given by d sine theta. That extra distance is going to be small because d is small. These angles are also kind of small, but in particular, d is small. And that distance is going to be, on the order of sort of like the extra distance there is going to be on the order of some number of wavelengths of light, which is, going to be at most a few hundred nanometers. So there's a very small additional distance here that the light from the lower slit travels in order to get to a position on the screen at angle theta than from the upper slit. And that extra distance is this extra distance here. Did that make sense?
Not really. Because
No,
if they both have the same angle theta, and then the L distance is the same for both perpendicular from the slit to the wall, and then there's some distance between perpendicular up to where they meet of a 90-degree angle, wouldn't a law of similar triangles mean that they're the same length?
Oh, I see. So I guess what you're saying is, if I draw the wall right here, then you would say that those two paths have the same length.
Yes.
which is true. Try to redraw this. Probably won't be able to do it on just a second. I think the issue might be that you actually need to have them sort of go to the same point far away. Yeah, I think it might be easier to see if, hold on a minute, so we can draw it on here. Can you see that?
Yes.
So here's a slit, and here's a screen, and so this is a little more exaggerated in the other direction, in the sense that you know, this slit with D is really much smaller than shown. But in this depiction, I think it should be a little clearer that this distance is equal to this distance, and this distance is a little extra.
Okay.
But when you zoom in, you know, on this region right here, these two lines, which I'm just going to highlight here with a different color temporarily, these two lines, you know, look like they're parallel. And that's what was drawn in the previous figure. But they're, strictly speaking, not parallel. By that?
Yeah.
You sure? Well, think about it. If you have any further questions, feel free to ask.
Is it just that when you zoom in so close, they look to be parallel?
I think they're just drawn to be parallel in order to make it, in order to justify using or saying that this is d sine theta. So, you know, at small enough angles, these two lines are effectively parallel, and therefore you can use trigonometry to figure out that d sine theta is indeed that delta r. And if they weren't parallel, then if you didn't assume they were parallel, then it'd be hard to make this. Could you even make a 90-degree angle here? Yeah, I guess you could. But then, you know, the definition of what the angle is would be a little bit tricky, because, you know, the angle here might not be equal to this angle here if these two lines, so this is the theta, if these two lines are not parallel. This line and this line are not parallel. So it's you're right. What we're making an approximation here, but it's a pretty good one because D is very small. The angles are usually pretty small. So the approximation we're making that the lines are roughly parallel and that there's an extra distance traveled that's d sine theta is not perfectly right, but it's pretty close. It's a good question. Any other questions? Okay. Thanks, everybody. We'll see you next time.
Bye.
Bye-bye.